Welcome to The Explainer. Today, we're diving into the ultimate balancing act, the anatomy of a spacecraft. Designing a vehicle to survive and, actually thrive in the universe's most unforgiving environment isn't just about bolting some metal together. It's a monumental task of resource management, risk calculation, and uncompromising physics. When you're sending millions or even billions of dollars into the void, every single decision carries massive weight.
All right, let's kick things off with a massive number, 34 billion joules. That huge figure is the explosive kinetic and potential energy required just to get a relatively small 1,000 kilogram spacecraft into low Earth orbit. To put that into perspective, that is enough energy to power a typical house for almost half a year, and it all has to be released in a highly controlled explosion right underneath your delicate, super expensive instruments. Crazy, right? So to figure out how we harness all that intense energy without completely destroying the mission, we're going to explore a few things today. We'll look at the ultimate engineering puzzle, the rules of the game, shaping the spacecraft, the anatomy of a spacecraft, and finally, the margin for error.
Okay, let's jump straight into part one, the ultimate engineering puzzle.
At the heart of every space mission, there's this fundamental divide. It's the payload versus the spacecraft bus. Now, the payload, that's the star of the show. It's the whole reason we're going to space in the first place. Your high-res cameras, your radar arrays, all that good stuff. But here's the thing. Those instruments are literally useless without the bus. The bus is kind of the unsung hero here. It's the life support vehicle that constantly provides the power, the precise pointing, and the thermal control required to actually make that science happen.
So how do we design this bus? Well, it happens in these highly integrated phases: documenting the drivers, determining the configuration, partitioning the subsystems, and establishing some very strict budgets. And why this specific loop? Because spacecraft design is fiercely, incredibly iterative. It's like a giant puzzle where every tiny addition ripples outward. Let's say the science team wants a better, higher-resolution camera. Okay, well that needs more processing power. More power means you need larger solar panels. Larger panels add structural mass. And more mass? Well, that means you're suddenly buying a much bigger, much more expensive rocket just to get off the launch pad.
Which brings us to part two, the rules of the game.
Every spacecraft is boxed in by these really rigid antagonists, things like mass limits, power consumption, cost, schedule, and orbit parameters. And out of all of these, mass is the absolute fundamental resource. Delivering literally anything to orbit is just astronomically expensive. And here's the kicker. It isn't a gradual cost increase. Hitting the mass limit of a specific launch vehicle creates this brutal step function in cost. If you go just a few kilograms over your limit, you don't just pay a little overweight baggage fee. You actually have to buy an entirely different class of rocket, which instantly tacks tens of millions of dollars onto your budget. No pressure, for sure.
All right, moving on to part three, shaping the spacecraft. So those strict rules of mass and power we just talked about, they directly dictate the physical shape of the vehicle, especially when it comes to figuring out how to point it. Engineers generally choose between two main philosophies here. First up is spin stabilization. This is literally spinning the entire craft like a top to give it passive stability. It's super reliable and uses almost no power, but as you can imagine, trying to aim a camera from a spinning top is pretty tricky. So the modern standard for observational missions is 3-axis stabilization. This uses active sensors and internal spinning reaction wheels to hold the payload perfectly, completely steady in space. You're basically trading higher complexity for just incredible precision. Now let's look under the hood in part 4, the anatomy of a spacecraft.
To manage all of these physical constraints efficiently, engineers partition the spacecraft into highly specialized subsystems. You can really think of them like the vital organs of a human body. First up, we've got the CNDH, which stands for Command and Data Handling. This is the brain of the ship. It operates the flight software, routes all the information, executes our ground commands, and crucially, stores the mission's valuable payload data in memory until it's ready to be downlinked to Earth.
But, a brain is totally useless if it can't communicate, right? And that is exactly where the TT&C system comes in: telemetry, tracking, and command. Acting as the mouth and ears of the spacecraft, this system provides that absolutely critical radio frequency link back to us on Earth. Transmitting data over millions of miles is heavily governed by the strict physics of antennas and transmitter power. Literally, without the TT&C mouth to speak, all that amazing science data would just be lost in the void forever.
Next is the thermal control system, which basically acts as the spacecraft's skin. Utilizing precision-placed radiators, multi-layer blankets, and internal heat pipes, this thermal skin protects all those delicate internal organs we just mentioned from wildly extreme environments. I mean, think about it. It has to simultaneously shield the craft from the baking 300 Kelvin heat radiating off the Earth on one side and the freezing 3 Kelvin vacuum of deep space on the other. It's a huge balancing act. Finally, we have the ADC, attitude, determination, and control. If we're keeping with the anatomy analogy, this is the inner ear and the muscles. The ADC system uses things like star trackers and sun sensors to calculate exactly where it's pointing in three-dimensional space. Then it flexes its muscles using spinning reaction wheels or thrusters to hold the payload right on target. Without the ADC, your shiny new billion-dollar telescope is really just a piece of metal tumbling blindly in the dark.
Which brings us to our final section, Part 5, the margin for error.
So how do engineers protect these vital organs against the frankly terrifying unknowns of space? Well, consider the typical mass distribution for a low Earth orbit spacecraft. The payload, again, the whole reason we launched the mission, only accounts for about 31% of the total mass. The remaining 69% goes entirely into the structure, the power systems, and all the support equipment required just to keep that payload alive.
Because every single gram and watt counts, systems engineers have to meticulously budget their resources. They calculate what's called the current best estimate for mass and power, but, and here's the trick, they don't give it all to the designers right away. They actually hold margin, extra unallocated mass, power, or propellant secretly in their back pocket. This contingency margin is literally the only way to solve the unforeseen design problems and weight increases that inevitably happen when a spacecraft goes from a nice, neat paper drawing to actual physical hardware.
But we really have to ask the ultimate worst-case scenario question here. What happens if a part fails? Remember, we're talking about a vehicle flying in a void where it can never, ever be retrieved or repaired. So a blown fuse or a stuck valve isn't just a minor inconvenience. It can literally be the sudden, catastrophic end of a decade of hard work. To combat this huge risk, engineers must make a brutal trade-off based on the mission's timeline and budget. Do they use a single-string design? Now, this is cheap and it's light, but it's highly risky because a single component failure ends the entire mission. Or do they go with a fully cross-strap design? This one is heavy and incredibly expensive, but it's highly resilient because redundant backup hardware can just be seamlessly switched in if the primary system dies.
It really comes down to this. Margin is your insurance, because you absolutely cannot retrieve a spacecraft once those rocket engines ignite. Leaving extra fuel, extra processing power, and extra mass in your design is the only reliable way to survive the inevitable surprises of space. Margin is the critical buffer between a wildly successful orbital mission and an incredibly expensive piece of space debris. So I want to leave you with this final thought to ponder. When you launch into the void, how much margin will you bet your mission on? Understanding this meticulous balancing act between capability, cost, and risk is what truly allows us to engineer our reach into the stars. Thanks for joining me for this explainer, and we'll catch you next time.